Hey everybody, Trey here. Welcome back to another video. We've just wrapped up our latest sequence of severe weather across the central and southern plains, and it was quite the doozy, with widespread severe weather impacting a bunch of folks from New Mexico over to Louisiana and up to Missouri and areas in between. And it did include some tornadic activity, although the tornado activity was a little bit underwhelming based on what was expected. Forecasts called for a wide swath of the central and southern plains to be under the gun for a significant tornado risk with several tornadoes possible. And that did not really come to fruition except in the early morning hours of November 3rd in central and southern Oklahoma. What was expected to be mostly just a squall line with a few embedded circulations quickly turned into a localized tornado outbreak, particularly in and around the Oklahoma City metro area. We saw 3 EF3 tornadoes occur in the early morning hours of November 3rd, one that went through the eastern side of the OKC metro, one that developed very near the NWS radar site, KTLX, and moved off toward the town of Harrah, Oklahoma, and then one just to the southwest of the OKC metro area near the town of Comanche that was associated with a pretty significant, robust radar signature. And so it was quite the unexpected sort of event, although some folks, including myself, were a little bit suspicious that we might see a bit of a nasty event there in the overnight hours. Even if it was just the squall line, we were expecting some very significant damaging winds and maybe some spin-up tornadoes in that line, but what actually ended up transpiring was quite significant, and definitely didn't see that coming ahead of time with multiple significant tornadoes like this in and around the Oklahoma City area. We're going to focus on this portion of the latest sequence in this video. We're going to go over the overall background pattern that supported the severe weather on the early morning hours of November 3rd, and we'll discuss how the atmosphere changed leading up to this tornadic activity and try to decipher why the atmosphere was so favorable for significant tornadic activity when the forecast didn't really suggest that that was going to be a possibility. So here you can see some damage pictures there. Very significant damage across the Oklahoma City metro area from these tornadoes. Again, all of these were rated EF3, as well as an EF1 that took place near Newcastle, Oklahoma. And here's some images from the Comanche, Oklahoma tornadic supercell that crossed into Oklahoma from northwest Texas. Some pretty impressive images there, including what appears to be twins as the storm moved off into near the Comanche area. So very impressive stuff. It was not quite expected, and we're going to try to show you why that was the case in this video. So without further ado, let's go ahead and get started. Just to show you how unexpected this was, at least based on forecasts, this was the SPC outlook from the morning of November 2nd, so the day one convective outlook on November 2nd. And just as a reminder, the day one outlook goes from 12Z on the day of to 12Z the next morning. So basically 12Z on November 2nd to 12Z on the 3rd. So this outlook does cover the early morning period of November 3rd, and it was just a slight risk with a marginal risk extending up to the Kansas-Oklahoma border, and our tornado risk was Oklahoma City and surrounding areas were just barely in the edge of this 2% contour here. The main tornado risk was expected to remain well southwest in parts of southeast New Mexico and west Texas, where a few supercells were expected to fire. Not a ton happened in that part of the risk area. A few supercells did fire, producing large hail, and a couple of brief spin-ups, but the main tornadic activity associated with the overnight stuff in Oklahoma was just in the very eastern tip of this 2%, and that didn't really change much throughout the day. This was the 1Z outlook, so the evening outlook on the 2nd, and not much had changed. That slight risk barely did extend to the Oklahoma City metro area, and we remained in a 2% here. And I'll put on the verification for you to show the storm reports. Most of the tornadic activity occurred just in the very edge of that slight risk and 2%. So quite an unexpected event based on forecasts, so we're going to try to discuss why that was the case going forward. Let's first start off by taking a look at the background meteorology behind this event. We'll start out, as always, at 500 millibars at 12Z, so 7 a.m. Central Daylight Time on November 2nd. And the first thing of note, as we talked about in our forecast discussion videos for that day, was this big old trough here across the west coast. But it was lagging significantly far back to the west. As we started the day, the axis was still well back here across California into Nevada, with most of the flow relegated to the backside of the trough axis. This means that the trough was still in the process of maturing, and it was going to take some time for this to really continue to dig down and eventually eject into the plains. That was not expected to happen until a couple days later. So we were really left in a little bit of no man's land, per se, in just this broad belt of southwesterly flow out ahead of the trough. I'll advance the loop here, and you'll see we do see the trough start to dig down into the desert southwest by late in the day on the 2nd, going into the nighttime hours. And we're just left with this broad southwesterly flow across most of the region, New Mexico, Texas, into Oklahoma and Kansas. We do see some strengthening of the flow throughout the day, up to about 50 knots or so, but really overall, again, the trough axis was still well back in here across the desert southwest into the Great Basin, so we were well removed from most of the forcing associated with this trough. And again, the trough was still in the process of maturing, so we were still a little bit of a ways off from getting the full impact of the trough across the southern plains. So we were going to have to rely on surface features and any embedded shortwaves within the flow to help us focus the severe threat in this particular event. Now, if we back it up to the morning, we do see a little bit of a shortwave here at 500 millibars situated across Arizona into western Mexico. Just a little bit of a subtle kink in the height contours there, but subtle but noticeable, and this was going to help us out in initiating widespread convection during the day across Texas and Oklahoma. And this was pretty widespread. This was starting in the morning on the 2nd. You can see a broad band of convection here from Kansas down into Oklahoma and West Texas, even down into eastern New Mexico. Lots of convection in this warm advection regime out ahead of this shortwave, but the shortwave was helping to add a little bit more forcing to what was a very nebulous, large-scale forcing pattern here. And this convection persisted through much of the day across these areas into North Texas. We had the line move through into central Oklahoma during the afternoon into early evening hours, with additional convection behind that. So we're going to come back to this in a second, see how it impacted the overall environment and how recovery progressed after this initial band of storms. But this shortwave was definitely an important factor in focusing the severe threat during the daytime out here across New Mexico into West Texas, and then during the night as it transitioned off to the northeast. I'll play this loop once again. You'll see if you track this shortwave right in here, you'll see it moves off to the northeast slowly during the day, and by late afternoon to early evening, that shortwave was somewhere in this vicinity here across kind of western Oklahoma to West Texas, western Oklahoma, down into north central Texas there. So we were right on time there, right ahead of that shortwave trough across northwest Texas and Oklahoma to initiate additional convection after the morning rounds of storms. Then going through the overnight hours, we see that shortwave really slowly move off to the east. This is at 11 p.m. or this is at 1 a.m. Central Daylight Time, starting to impinge upon central Oklahoma there to help allow those storms to persist. So that shortwave, very important in helping us increase the forcing in what was a very nebulous pattern as far as large-scale forcing for ascent goes, at least in the mid-levels of the atmosphere. We can see this shortwave perhaps even more clearly at 700 millibars. Keep your eyes focused there on the West Texas to Oklahoma corridor. By early evening, you can clearly see the kink in the height contours there over the Texas Panhandle down into northwest Texas. And then over the next several hours, it moves right into central Oklahoma, right on time ahead of the tornadic activity across central Oklahoma, right smack dab in the exit region, right out ahead of that shortwave trough, was where most of this activity occurred. Because the mid and upper level trough and its associated forcing were lagging a bit farther back to the west, we hadn't really seen a robust low-level response, and that was true for much of the day on the 2nd. Here we are at 12Z on the morning of the 2nd. Not much going on across the central and southern plains. Big old ridge of high pressure out here across the eastern U.S., with not really much going on to the lee of the Rockies in terms of surface low development. Maybe a weak cyclone out here across West Texas into north central Mexico, but not much going on at all, and this would persist through much of the day. You see here as we go forward in time, we really didn't see any sort of surface low development, any more robust surface low development until later on in the period across eastern Colorado. When this is at midnight Central Daylight Time, we finally start to see some evidence of a little bit of consolidation or tightening of a surface low there in eastern Colorado, which would help allow those surface winds to back and strengthen a little bit across the southern plains, which was needed because of that early convection. That early convection was quite robust, and early is probably not the best word to describe it. It persisted through quite a bit of the afternoon. Here again is that wide view of the radar. Big old band of storms here during the morning hours from Kansas all the way back into eastern New Mexico, and that continued through much of the day, especially across central Oklahoma. We're not even through to 3-4 p.m. here, and then finally the band starts to come through the Oklahoma City metro area. This is just after 5 p.m. The band is just going through the OKC metroplex. That's extremely late in the day. As we've talked about before, usually if you have any more early convection, you want that to be out of your area early on in the day, usually in the morning, to allow for some surface heating and clearing behind it to build that instability back up and allow the atmosphere to recover for severe storms later. This is at 5 p.m., just after 5 p.m. We're still seeing robust storms moving through central Oklahoma. So we really needed... And behind that was cloudy and additional storms developing back here to the west as well. Not going to get much time at all to allow the atmosphere to recover. So we were going to need strong, low-level warm, moist advection to happen to really allow this atmosphere to recover ahead of this second batch of storms that was moving into Oklahoma. But that's exactly what did happen, especially once that surface low started to develop. Now here is our raw surface data. At the start of the period, our winds were already out of the southeast. A few days before, they were out of the north, thanks to a previous frontal passage from our previous severe weather event to end October. A cold front had come through, had switched the winds to northerly here, had pushed the moisture all the way down here, but we had those winds flip around pretty quickly to southeasterly, allowing for a pretty robust low-level moist air mass to reside across the region. Dew points in the low to mid-60s across much of Oklahoma, with more robust moisture across Texas. Dew points in the mid to upper 60s to the south of the Red River, and even some 70s there across east and southeast Texas. So robust moisture was sitting not far away, and it wasn't going to take much to get that more robust moisture off to the north. Now, still, you had to worry about that antecedent convection there across Oklahoma, and you can see what the impacts were from that convection. Temperatures to start the morning in the low to mid 60s there across central Oklahoma. We do get some warming by afternoon, temperatures approaching 70 there by about 2 p.m. or so across central Oklahoma. So temperatures had warmed, but you can see what happens as that initial line comes through. Temperatures plummet into the low 60s. So there was certainly a little bit of a convectively reinforced boundary, perhaps an effective warm front that was starting to set up across central Oklahoma, a boundary between the rain-cooled air to the north and a little bit more unsullied air to the south. And that unsullied air, wherever that was going to end up, the northern bound of that, which was demarcated by the boundary, was going to be our best shot to see any potential severe activity that was surface-based going into the evening and nighttime hours from the second into the third. And that's exactly what we did see. Those winds continued to strengthen and back as that surface low started to develop across eastern Colorado. We started to see a little bit of a strengthening of the low level and surface flow here to out of the south-southeast. And we started to see a little bit of a warm front develop across central Oklahoma. It's a little bit difficult to tell, but we do have some subtle clues. This is the surface data from 1 a.m. Central Daylight Time on November 3rd, and we see a little bit of a boundary here developing maybe just on the south side of the OKC metro, draped off to the east into eastern Oklahoma. We see a little bit of a wind shift across the boundary, winds perhaps a little bit more easterly on the north side of the boundary, a little bit more southerly component to the south, more southeasterly flow on the south side of the boundary. We also have a little bit of a temperature gradient, the rain-cooled air off to the north, with temperatures in the mid-60s across northern and northeastern Oklahoma, with temperatures in the 70s to the south of the boundary. We also have a little bit of a dew point gradient as well. Dew points in the low to mid-60s across northeastern Oklahoma, with dew points approaching 70 to the south. 70 at Ada, 68 at Ardmore, 65 there at Shawnee, which appear to be right near the boundary. So it was pretty clear that there was more robust, more unstable air making its way quickly up from the south to the south of the boundary. And that boundary was going to be the demarcation where storms might have the tendency to be elevated off to the north compared to more surface-based to the south with more of that all-hazards threat. One more thing, if we look at our actual surface analysis here from the mesoanalysis page from the SPC, we can see a little bit of a kink in the isobars here across south central into eastern Oklahoma, indicating where that little bit of a pressure tongue was and perhaps where that effective warm front was located. So there certainly appeared to be some sort of boundary draped right across the Oklahoma City metro, perhaps just on the southern side of the OKC metro into eastern Oklahoma. And again, as those storms fired up to the west, it was going to be critical to watch where that boundary was going to set up, as the more unstable air and a greater potential for storms to be surface-based with all hazards, including a tornado threat, was going to be to the south of this boundary, and any storms that, of course, interacted with the boundary itself would have an enhanced tornado threat as well. Air mass recovery across central Oklahoma was going to need to be quite rapid to support any type of severe weather overnight, given that this was the observed environment at Norman at 0Z, so the evening sounding on November 2nd. Not supportive really of any kind of severe weather, very limited, almost zero instability here. 64 over 64 at the surface, but a very strong capping inversion just above that, with a very weak lapse rate profile due to the saturated nature of the environment above that. So a very, very poor thermodynamic profile. And our wind profile, not really favorable for any type of significant severe weather, very limited low-level shear. And deep layer shear was on the margins for supercells, only about 30 knots of 0 to 6 kilometer shear, which is certainly marginal for any type of supercell activity. So really not an environment that you'd expect to see any type of severe weather, especially going toward the hours after sunset, when we don't have surface heating to rely on to really bolster that instability. But nonetheless, we still saw a rapid improvement of the environment after 0Z. Here is a series of RAP model proximity soundings at Norman from 0Z to 6Z, basically right before the tornadic activity began. And we start out as very similar to what the observed sounding showed, but watch what happens to both the thermodynamic and the kinematic profiles here over the next several hours. We see a pretty rapid increase in instability, as well as low-level and deep layer shear, to now an environment very supportive of severe weather. This is at 6Z, right before the tornadoes began. Still somewhat of a skinny cape profile, but now more than adequate to support robust updrafts. About 1,100 joules per kilogram mixed layer cape, 68 over 65 at the surface. That capping inversion had certainly decreased in intensity here. Still a little bit of a warm nose there, but look at our low-level shear. We've talked ad nauseum about how low-level shear, strong low-level shear, can help overcome somewhat more meager thermodynamics in the low levels, and we have certainly a profile that was helping out with that. Now up to over 300 meters squared per second squared effective storm relative helicity. Very impressive turning, veering, and strengthening of the low-level winds with height. Strong clockwise curvature in the low levels of the hodograph, with now over 50 knots of effective bulk shear, more than favorable for supercells. So we very quickly, in a very short amount of time, without the aid of surface heating, were able to go from this, an environment not favorable at all for really any type of robust weather, to an environment that was certainly capable of producing significant tornadoes. And the reasons for that was very strong warm moist advection. You can see as we start at 0Z, 64 over 63 here. The observed was 64 over 64. And then we go over the next several hours, we increase both the dew point and the surface temperatures quite efficiently. Temperatures up toward the 70-degree range, and the dew points up now in the mid-60s. So we had a warming and moistening of the low levels of the atmosphere, helping to really negate the impacts of that low-level inversion and help bolster instability. We also may have had a little bit of a cooling of the mid-level temperatures here. We start off with somewhat warmer mid-level temperatures. Keep your eyes focused right in this portion of the sounding, and then we go over the next couple of hours. We see a little bit of a decrease in those mid-level temperatures, leading to a little bit steeper lapse rates in excess of maybe 6.5 degrees Celsius per kilometer in that layer. And that could have been due to the advance of the shortwave and the impinging of the shortwave into the region, bringing in just slightly cooler air aloft to help also bolster instability. There also may have been a little bit of a northward advance of the warm front over this time. As that low-level cyclone developed across eastern Colorado, the low-level flow strengthened, perhaps allowing for a little bit of a northward push of that warm front into central Oklahoma, really into the Oklahoma City metro area. And that also, of course, led to increasing low-level shear. By this time, at 6Z, the low-level jet was very strong, about 40-plus knots or so of flow at 850 millibars, leading to intense low-level shear, favorable for significant tornadoes. So this was key in this event, the rapid improvement of the environment over just a few hours' time, not due to surface heating, of course, but rather due to very intense low-level warm moist advection on that increasing low-level flow, helping to bolster the instability within the environment, helping to push that warm front north into the Oklahoma City metro area, and allowing low-level shear to strengthen, creating an environment favorable for significant severe weather. Now the question was how storms would progress through the night. Would there be discrete supercells in the open warm sector, or would we just be dealing with a nasty squall line with embedded circulations? As the initial band of morning convection moved off to the east into Oklahoma and northwest Texas, additional storms developed on the higher terrain of eastern New Mexico and along the outflow boundary from that initial morning band. You can see that fine line draped down to the southwest here across the Texas South Plains, with quite a few storms developing along and near that boundary. Very clear in surface data as well. This is at 18Z, so 1 p.m. Central Daylight Time, and you can clearly see the wind shift there emanating from that band of storms going down from southwest Oklahoma into northwest and west Texas. The convection back to the west congealed into more of a clustered linear mode with time, and as we discussed earlier, the outflow boundary from the initial band of storms moving across Oklahoma became the effective warm front, separating the stable, rain-cooled air to the north with the more unsullied open warm sector to the south. And that warm sector was fairly broad. If we look at our surface data just after 0Z, you can see that the 60s dew points extend from basically northwest Texas all the way out to the east in through at least the Ozarks there of Arkansas into Louisiana. And so we had plenty of real estate for there to possibly be open warm sector supercells. We just needed a couple things to come together for open warm sector supercells. Typically, you need some sort of forcing that overspreads the warm sector, and we had that in the form of the shortwave trough we discussed earlier. You need the open warm sector to be quite uncapped so that updrafts don't really struggle as they go up in the open warm sector, and we had that in spades. If we go to some of our soundings here, this is the Midland-Odessa sounding, so back out in here across West Texas. You can see fully uncapped there, lots of instability, and a totally uncapped air mass moving over to the east to Dallas-Fort Worth. Not quite as much instability, but mostly uncapped as well. Not really any notable warm noses impeding instability there. So our warm sector was basically all uncapped going into the evening and nighttime hours from the 2nd into the early morning on the 3rd. And the third thing that we need is we need some sort of focus, and that usually comes in the form of confluence bands. And in our raw surface data here, as we go forward with time, we don't really see much in the way of confluence bands setting up. But if we zoom in and look at our Oklahoma mesonet data, which is a lot more high resolution, this is a surface plot from just after 1 a.m. or 6Z on the 3rd, and you can clearly see a confluence band here. Back out to the west, this was where our band of convection coming in from the west was located. So that was our line of thunderstorms moving across central into southwest Oklahoma. But look out to the east of that. You can see a clear area of subtle convergence stretching very near the Oklahoma City metro area and down to the southwest into southern Oklahoma. Winds to the west of this boundary just ahead of the incoming line, more out of the south or south-southwest, with much more southeasterly flow out to the east. So that was a clear sign that we had a confluence band setting up across this area, stretching from North Texas into central Oklahoma, and that was able to provide a more subtle focus for supercell development along that boundary. And sure enough, with time, by about 2Z or so, we started to see a lot of convection firing up here in northwest Texas, and eventually it did sort of focus along that confluence band with multiple supercells moving to the northeast into central Oklahoma, right along that confluence band ahead of the incoming squall line to the west. Here's a bit of a closer view from the KTLX radar site in Norman. Multiple supercells traversing this corridor. This was the first one of note that moved up just to the southeast of the OKC metro area, produced what appears to be a very brief tornado as it approached I-40. You can see it wrap up there really nicely. It did have a very brief debris signature in the correlation coefficient product, it appears, but this tornado has not been confirmed, and if anything, it was quite brief. But we did have multiple supercells to the south. After this one crossed the warm front and dissipated, lost much of its structure, we still have these supercells coming up from the south in the warm, moist air mass within the warm sector. This one would be the one that traversed into the eastern OKC area and produced the EF3 damage there. And then this one would become eventually the Harrah EF3 tornado producer. You can see that first lead supercell, as it approaches the metro area, takes on a very nice hook echo appendage just to the north on the east side of OKC. Very classic hook echo right there, nicely wrapped up supercell with a tornado right at the tip of the hook. This one coming up from the south would be our next tornado producer near the metro. That would kind of putz around a little bit until it got to near the KTLX radar site, which is right in here, at which point it wrapped up pretty nicely and then produced a very impressive signature with a debris ball at the tip of the hook. We'll take a closer look here in just a second, but overall a very classic looking supercell right there. And then backing up a little bit, once again, the supercell to the south coming out of Texas. This was our Comanche supercell that produced the significant tornadoes down there. And then eventually everything was overtaken by the squall line coming in from the west, and we still had a few circulations that remained within the line as it moved off into eastern Oklahoma. One of the more interesting features of this outbreak was the fact that we had multiple instances of merging mesocyclones induce tornadogenesis. Perhaps the clearest example of this was with the Harrah tornadic supercell. This is some data from the TOKC radar, the terminal Doppler radar at Will Rogers International Airport in OKC, looking into the Harrah supercell. And this was before tornadogenesis occurred, and we have very clear evidence of two separate mesocyclones in close proximity to one another. You see two separate appendages here, two separate hook echoes associated with rotation. One here just to the northeast of Hall Park, and one here just off to the east of that initial circulation. Watch what happens here as we go forward in time. Harrah is up here in the top right corner of the image. As we go forward in time, watch what happens. These two separate appendages become one just south of Interstate 40. As a result, we see the rotation intensify pretty rapidly, and we see tornadogenesis occur up here west of Nuwala. We can see this on the actual KTLX radar as well. The only issue with KTLX is this basically happened right over the KTLX radar site, so we have a little bit of a gap in the data right where the cone of silence is located. But if we go here to our radar data, you'll see that we have those two separate appendages here, one right here, one over here, just to the east of the initial one. And as it goes over the KTLX radar site, we see a little bit of trouble depicting things there. But as we emerge on the northern side of the radar site, we don't have those two separate appendages anymore. We really have one supercell with one single hook echo, and then we see tornadogenesis to the west of Nuwala there. One side note here, very intense debris ball associated with this tornadic circulation here. You see the very much enhanced reflectivity at the tip of the hook, coincident with the strong tornado vortex signature there in velocity. So a very clear example of a debris ball there that was quite persistent as the supercell moved off to the northeast, and that couplet stayed very, very strong near Harrah. But this was a very clear instance of mesocyclone merging, two separate mesocyclones merging to become one and induce tornadogenesis. If you recall, we talked about this in one of our recent case studies on the April 30th, 2024 case in southwest Oklahoma, where we had the big Hollister, somewhat surprising Hollister, Oklahoma wedge tornado after dark. And that was a very similar case as well, although in that case, we had one single supercell with dual mesocyclones. Here it appears that we had two separate supercells here. I'll put it back on the TOKC radar so we can see it a little bit more clearly. But it appears that we had actually two separate supercells here with two separate mesocyclones. You can see that the reflectivity here is kind of separated between these two appendages. So I believe these were two different supercells here in close proximity to one another. But the idea is the same, that we had these two mesocyclones that were clearly separate at first, and then eventually they merged into one. And then we got one lone supercell with one appendage, and that induced tornadogenesis. There was also evidence of merging mesocyclones inducing tornadogenesis with the initial supercell that produced the EF3 in East Moore and southeast OKC along Sooner Road. Here's some imagery from KTLX of that supercell, and again, right away, you can see two different appendages here within this supercell associated with two different mesocyclones. One here right over Newcastle, and one down here to the southeast of Newcastle, southwest of Norman. So two separate mesocyclones, two separate appendages, and as that supercell moved off to the northeast, we see it merge into one single mesocyclone, one single supercell with a well-defined single appendage there, and you can see the yin and yang starting to come together, the outbound strengthening, the inbound strengthening as well, a strong rotational signature developing, and then right over East Moor we see a strengthening of the vortex signature into a tornadic circulation. So very interesting stuff here. Again, this has been documented before, but is not all that common, but we certainly had multiple examples of this with this outbreak. The Comanche supercell also may have had some of this merging mesocyclone madness that induced tornadogenesis, but it's not quite as clear of an example as the first couple supercells we went over. You do see multiple appendages here prior to significant tornadogenesis southwest of Comanche, but nonetheless, this was a very potent storm. You see here, as it approaches Comanche, we see a very intense circulation develop, and there were multiple points along this storm's life cycle where we saw two circulations in progress at once. Here's an example of one, the main circulation, very strong circulation just southwest of Comanche, and then a smaller but very tight tornadic circulation just to its southeast along Highway 81. So very impressive storm. We had photographic evidence of this phenomenon. You see here in this photo, very stout cone tornado there to the left with one back in here that's a little bit more faint, but still quite clear that we had two circulations in progress at once. So very impressive storm. And we also saw perhaps some influence from the squall line back to the west. If you recall, on our April 27th, 2024 case study where we had those supercells from Sulphur, Oklahoma, off to the northeast near Holdenville, we had a very similar situation where the squall line actually was able to give a little bit of a nudge to the lead supercells to aid in tornadogenesis. Perhaps the same thing happened here. You see the squall line closing in from the west, back out in here, our supercell prior to tornadogenesis, not showing much of a tight mesocyclone there, but as the squall line closes in, we see an uptick in the intensity of the circulation, and then we see tornadogenesis there southwest of Comanche as the squall line closes in. So this very well could have played a role in, the squall line very well could have played a role in nudging tornadogenesis here with this lead supercell, as described in some recent research from Cameron Nixon. I'll put the paper down in the description box below, but this is perhaps another good example of this sort of nudging phenomenon from the QLCS back to the west, inducing tornadogenesis in the lead supercell. So that's going to wrap things up for this video. Hopefully this enlightened some of the reasons why we got such significant tornadic activity in the early morning hours of November 3rd across central and southern Oklahoma. This event just goes to show how fine of a line we walk sometimes between no warm sector activity at all to a lot of warm sector activity with significant tornado potential. In this case, the environment really rapidly changed and rapidly improved in the few hours leading up to this tornado outbreak from a really an environment that was not capable of supporting really any severe weather at all to one that was capable of supporting significant tornadic supercells. That came together very quickly. Once that came together, all we needed was an impetus for prefrontal warm sector development, and that's exactly what we got. Our warm sector was broad, it was uncapped, and we had just enough forcing from the shortwave moving in, as well as that confluence band in the open warm sector, and that's all you need to really get robust supercell development in the open warm sector, and then it was off to the races once that environment became pretty favorable for significant tornadoes. So just a very interesting event overall. Definitely thoughts and prayers with the folks here impacted across the OKC metro area and surrounding areas of southern Oklahoma. But this was certainly an event that is worth studying to become better at forecasting these events in the future. So with that, thanks for watching, and we'll see you in the next video.